Greenwich, London. And one or two bits and pieces about Simon to explain why he's pretty good at what he's going to talk about. So he graduated the University of Oxford in 1971 and then went to University of Birmingham. That's actually a very important place as far as radar is concerned. You could say microwave radar really started there. But anyway, and there he obtained an MSc and a DSc in various years, and then a PhD from the CNAA in 1987. But Simon, and some of you know this already, was Deputy Scientific Director and Technical Fellow in Thales, UK. But he actually was, he wasn't a EMI man, so and those of you who know the history will appreciate really what that means. And he worked on a wide range of radar and electronic warfare projects with particular research interest in maritime radar and sea clutter. But he's author and co-author of about 90 journal and conference papers, 2 books on sea clutter and several patents. And he's got an MBE in 1996 for services to the UK defence industry, and he's a fellow of the Royal Academy of Engineering, fellow of the IET, fellow of the IMA, and fellow of the IEEE, and he's missed out one thing. He's also, like me, a radio amateur, so he's a member of the RSGB as well. So, anyway, it's my pleasure to introduce Simon. Over to you, Simon, when you're ready.
Good. I'm going to talk to you about Moonshine. So, by way of introduction, then modern radar jammers use very complex systems to monitor the radar environment, to identify potential threats, and to determine an appropriate electronic response. If their aim is simply to deny the enemy the use of radar, the most effective form of jamming is noise jamming, which retransmits noise-like waveforms into the frequency band used by the radar. If the exact frequency is unknown, then a broad band of frequencies is used, what's known as barrage jamming. However, it will be obvious, more or less, to the enemy that jamming is taking place, which may not always be a desirable outcome. With modern jammers, they use techniques called deception jamming. We're aiming to create realistic false targets. And this is a more sophisticated form of attack, and the enemy may not be aware, initially at least, what is happening. So, against pulse radars, then modern systems use repeater jammers. These receive individual radar pulses and temporarily store them for a few microseconds or less in a very high-speed digital RF memory. They then retransmit them with added modulation in time and frequency as desired. And their aim is to recreate in the radar a false target or a collection of targets in order to distract or deceive the radar operator. Now that's today, but as we shall see, radar jamming is not new, and it's almost as old as radar itself. And I'm going to talk about the very first British radar jammer, which was in fact a pulse repeater jammer that entered service in World War II in 1942. So the first operational radars in the UK were developed in the late 1930s with the Air Ministry Experimental Station Type 1, later known as Chain Home, which entered service in 1938, before the start of the war. The first experimental monostatic airborne radar flew in 1937, RDF2. And the first operational airborne radars were deployed very soon after the start of World War II in 1939. And here we can see an ASV Mark II, I'll talk a bit more about that later on a Wellington bomber, probably in about 1942. I've mentioned chain home. This is Ames Type 2, which is chain home low, which was a VHF radar aimed at getting at the lower coverage over the sea. And this is the ground control intercept radar from 1942, which was a 360-degree scanning radar. These had fixed beams, limited steering. These had to be steered initially by an operator who could steer the beam and look for a target. So these latter three, these ones here, were used for air defense, and the ASV system here was used for hunting U-boats and ships. So by 1941, there were very many British radars in service. But radar countermeasures were a very low priority. And indeed, they had very limited understanding of the capability of the Germans in radar. Then in 1942, there was a very rude awakening in the form of what became known as the Channel Dash, when two German battle cruisers escaped from Brest up the English Channel back to the safety of German ports. And they did this under cover of very heavy jamming against the British radar coastal defences. So, and as a result of this successful jamming, the Radar Countermeasures Division of the Telecommunications Research Establishment, led by Robert Coburn, were then able to establish radar countermeasures as an essential war requirement. Two jammers aimed at the German air defense radars along the coast of France were rapidly developed, and they were airborne, flown in aircraft. One was a barrage noise jammer called Mandrel, and the other was a pulse jammer called Moonshine, which is the subject of the talk today. So as I mentioned, during 1939 and 1940, there was really very little knowledge of German radar capability. And in fact, many doubted if the Germans had radar at all. However, there were increasing reports from spies, interrogations of prisoners of war, and intercepted radio traffic suggested that they must have what was known in the British as RDF, radio direction finding, or at that time in Germany as DT, decimeter telegraphy. And it was thought from interrogation of spies, prisoners of war and reports, that one of these systems might be called Freya. And the hunt was on from then for pictures of these systems and indeed reception of their signals. And a breakthrough came on the 22nd of February 1941 when two Freya radar stations were photographed at Eaudeville in France. A flying officer, Manifold, took these pictures, and you can see here are these two radars with large vertical arrays. I'll show in more detail what they actually look like, and pointing obviously in different directions. So, and indeed, the first signals from these radars were actually received just a few days later, and they were detected on a frequency of about 120 megahertz, or megacycles a second, as they would have called it in those days. And on the 5th of December 1941, further pictures of a radar installation were taken at Cap d'Antifer, near Le Havre, in northern France, in a village called Bruneval. These showed a Freya, which we can see up here, and another set up here, which turned out to be a Würzburg. And this was a shorter range fighter control radar. and this was the long-range air defense detection system. So it was becoming clear from this and from other information that the Germans indeed had radar, and by early 1942 a much clearer position was being developed. And this culminated on 27th to 28th of February 1942 in the Bruneval raid, when British commandos captured an almost complete Würzburg, dismantled it, took it back on a submarine. It was becoming clear then to all that the German air defense system was quite extensive and comprised long-range Freya surveillance radars and these shorter-range fighter control radars at the Würzburg. So what was going on in 1942? The Germans had occupied France, Belgium and the Netherlands, and the RAF were attempting to gain air superiority over France. It was known from aerial reconnaissance and from signal intercepts now that there was a chain of these coastal radar stations as shown on the map here. So each of these names here is a radar station. And each of these stations had one or more long-range Freya air defense radars, were operating at VHF, and the shorter-range Würzburg radars, fighter control radars. And they were spaced about 25 to 50 miles apart. And it was decided at this stage to try and spoof these Freya systems using airborne jammers in order to divert German fighter defences from real bomber raids coming in another direction. So they wanted to jam the Freya. It operated in a frequency band covering a range of spot frequencies for different installations between 119.5 and 128 megahertz. The Allies hadn't captured any examples, and other parameters had to be identified either from photographs that were able to be taken or from signal intelligence reports. And the figures shown here, the power and so on, were estimated at the time, and they were approximately right. It actually had a peak power of about 10 kilowatts and a pulse length of 2 microseconds. And it could detect a fighter aircraft out to about 120 miles. Then you knew this from intercepted radio reports. The Würzburg here was used for gun laying and fighter direction, was on a higher frequency, on about 570 megahertz. And it had a shorter range capability than the Freya. So the important thing was to understand what its range capability was, which was about 35 miles against a fighter aircraft. And so these jamming aircraft, that we're going to talk about in a minute, had to keep out of the range of Würzburg while they were jamming the Freya, so that they weren't rumbled. And so here are some more detailed pictures of these radars. Here's a Freya. You can see 2 antenna arrays, 6 vertically polarized dipoles in 2 rows with a mesh reflector at the back. And this is the transmitter array, and this is the receiver array. And on the right here is a Würzburg, and they were also starting to introduce giant Würzburg, the Würzburg Riese, which is a much bigger antenna. It had about double the range of the Würzburg. But these, at this stage, early stage, were still quite rare. And here's just a more detailed example of the one version of the Freya. This is the Limber Freya, which was transportable. You can see the sort of support legs here, and the cabin here for the operators. You can see clearly the dipole arrays and the reflecting grid, and you get an idea of the size. So it's about 6 meters by 2.5 meters for each array. And here is the operating cabin and main display unit. Here you can see 2 seats for the two operators, handles for steering the antenna. They were in the early versions, they would simply steer the antenna left and right and go for maximum signal to get a bearing on a target. Much later on, they introduced sort of a split beam method, sort of sequential lobing, if you like, but not at this stage. And here is the display unit. Characteristic of most of these German radars, they had absolutely tiny displays. They had a 2.5-inch cathode ray tube with a magnifying glass on the front. So what we're seeing here is the magnifier, and at the back here is this little tiny CRT. And they were always very scornful about the British. Far too big, their equipment, they said. So just a recap of the parameters. What we shall see is that these were the parameters at the time. The very early systems had a PRF of 1 kilohertz, which would only given 150 kilometers unambiguous range, and these were later reduced to 500 to give them no danger of getting second time round returns against targets, and 2 IFs and a relatively narrow bandwidth. And you can see the beam width of these things is pretty broad, but not fractions of a degree or anything like that. So we're going to jam this radar. So it's worth visiting briefly the JAMA radar equation and apply it to Freya. So the pulse jammer on an aircraft what it's trying to do is replicate the same sort of signal as the radar would be receiving from the aircraft itself. So it's a protection jammer, if you like, and we're going to put out a stream of these like-sized targets at longer and longer ranges behind the jammer. So the jammer has an effective radiated power, which is its peak power times the antenna directional gain, PJ and GJ. But the power reflected back from the aircraft itself would have been about a similar sum. This is the ERP of the radar, but then it's gone out over a range of R, so it's spread out over 4 pi steradians, and so the power density at the aircraft is the ERP divided by 4 pi r squared, and then the radar cross section of the target, the aircraft, is sigma, which gives the power which is then being radiated back towards the radar. So this PJ, GJ, the ERP of the jammer, there's got to be some fraction K of the actual power of the ERP of the radar. And we can see that if the radar cross-section was 100 meters squared, a fairly largish aircraft, and R was 35 miles, which is the closest we were going to get before we got into the range of the Würzburgs, this factor K is minus 86 dBs, which is a lot lower than the radar power. So the Freya had a 10 kilowatt peak power, about 13 dB antenna gain, and so the jammer, we'll see they just use a simple vertical dipole below the aircraft. So it had a gain of about 3 dBs, so with this very simple powers, the jammer then only requires a peak power of about 0.5 milliwatt in order to replicate the return from the aircraft. And at longer ranges, even less power would be required. Now that's actually at the antenna. These systems were not that efficient, so there have been lots of feeder losses and propagation variations, so they would have had a slightly more margin than 0.5 milliwatt. But even then, even with all these propagation and feeder concerns, jammer powers are only milliwatts were required in order to reproduce a signal of similar cross-section, and that's the power, as you can see here, the power from the jammer needs to be proportional to or vary with the range, or the inverse square power of the range. So it needs to essentially vary its power according to the signal that it receives in order to be realistic. And to be absolutely sure, they flew calibration flights to establish the signal levels achieved by an airborne receiver at different heights and ranges. And they estimated that with a receiver with a vertical quarter wave dipole would receive a maximum signal of about 30 millivolts measured at the antenna at the desired minimum range. And they could detect signals beyond 100 miles. And as I mentioned, the retransmitted pulses had to have an amplitude proportional to the received pulses. And it was then estimated that a signal gain of about 34 dBs, a voltage gain of 50 in our little repeater system, was going to be required to replicate the return from a fighter aircraft. So with 30 millivolts received, 1.5 volts transmitted, that reflected a maximum power of 30 milliwatts. And that would have been generous. But you also had to take into account, what I'll just show you on the next slide, this is actually some published results from the time of their signal strength measurements that they made, flying at 10,000 feet in an aircraft with a little dipole receiver, and the dots here are the received signals, and these are theoretical curves for different heights. They were at 10,000 feet, but you've got a maximum, minimum, depending on exactly what's happening to the signal in terms of multipass reflection from the sea surface and so on, which would have also caused fluctuations and variations. But you can see that the measured signals fell quite nicely within the expected range, which was gratifying. So the idea was to fit this jammer that we were going to build into a group of aircraft and fly them at about 10,000 feet towards the enemy air defense systems, starting at over 100 miles. And then each of these systems, Moonshine they were called, would transmit an extended pulse of up to 50 microseconds long, and I'll show you what these look like in a minute, on receipt of a radar pulse within the band to which they were tuned. Each of their receivers had a bandwidth of about a megahertz, and so about 8 separate sets, Moonshine sets, had to be flown at once in order to be sure to cover the band of frequencies likely to be used by Freya. And so this is how it was done. We've got here a receiver in the jammer, a pulse unit used to generate the extended return, and a transmitter. So each receiver here was pre-tuned on the ground to a spot frequency, and then a number of spot frequencies to cover the total band of Freya frequencies. If a pulse was received, it was through this high-pass filter, which I'll mention in a minute, that was ready to stop spurious signals coming in on the IF, which was 20 megahertz, and triggering a response. But basically it comes in, is mixed down to an IF of 20 megahertz, 20 megacycles a second, amplified through a diode detector, and then a cathode follower buffer out to the pulse unit. You'll also notice here connections to headphones. These weren't used on these early sets. These were sort of automatic systems flown in the aircraft. But later on we'll see that this was actually quite an essential part of later instantiations of these systems. So a pulse received on the appropriate frequency was sent to the pulse unit here. There was a limiter to limit it to maximum 30 volts input, a short delay, and then this triggered a master flip-flop with which I just put out a pulse with a length of up to 50 microseconds. And this again could be adjusted on the ground, not more than 50, I'll explain about that in a minute, but a preset response. And then this would trigger a series of oscillators in the pulse unit. These were transitrons, which is essentially a single valve multivibrator, with running in parallel with a slightly lower frequency neon oscillator. And these were all running on a frequency of about 300 kilohertz, but all slightly different frequency and slightly different phases being changed by these neon sawtooth oscillators. So giving a mixing, continuously changing mixture of signals around about this 300 kilohertz frequency. This signal was then went out through an amplifier which determined the depth of modulation that they were going to apply, and I'll give you some examples of that in a minute. But if they were trying to replicate a large number of aircraft, it would be fluctuating a lot more, the signal, than just a few aircraft. It's worth just thinking about these numbers, 50 microseconds and the modulation depth and so on. You must remember that the radar bandwidth of the Freya was less than a megahertz. And so individual targets spaced less than a couple of hundred meters apart or so would not be resolved. So you're not trying to reproduce individual little target responses. Over a 50 microseconds, which is about 4.5 miles, the radar, if you've got a stream of aircraft coming in, the radar would have seen just a continuous signal of fluctuating returns. And this extended signal was increased in amplitude according to the magnitude of the received signal. There's a memory automatic volume control here, so that was so that the weaker signals at longer range would have lower jammer power transmitted. And then this was sent to the transmitter, and also the pulse unit suppressed the receiver when it was about to transmit and turned on the transmitter oscillator. And here is the transmitter, and this it was an independent transmitter, but the idea was that the transmitter was set to approximately the same frequency as the receiver. Nothing too, as best they could. But it actually used a frequency doubler. So this is the transmitter local oscillator here, operating on 5965 megahertz. This is keyed from the pulse unit, and then goes into a frequency doubler amplifier, which is then anode modulated by this fluctuating signal to produce our up to 50 microseconds long pulse. And then out to the transmitter, which was just a little quarter wave dipole. And the aerial was connected also directly to the receiver, so the main protection was that the receiver IF amplifiers were shut down whilst you were transmitting. It's all pretty low power stuff. And the high pass filter to stop 20 megahertz signals coming in and triggering the receiver, the pulse unit. So in 1942, Mandrel and Moonshine were fitted to special duties flight, Bolton Paul Defiant aircraft. This would later become 515 Squadron of Fighter Command. This Bolton Paul Defiant was originally intended as a night fighter, or a day and night fighter, to attack incoming bombers. But when they designed this aircraft, they didn't think that the bombers would have fighters protecting them. And so the idea was you would simply fly up underneath the bomber and give him one with the gun from underneath. But they had no forward guns at all and couldn't protect themselves. And so once the bomber stream came in with fighter escorts, they were useless. So they were taken out of service as day fighters. They had a bit of a longer life as night fighters fitted with airborne intercept radar, but again were not ideal at all, and soon phased out. But they did have a continuing life in this special duty squadron fitted with Moonshine. So this is what the kit looked like. It was built in 3 boxes. So you've got the power unit, power supply, an 8 high-frequency unit with the receiver and the transmitter, and then the pulse unit here. And I've zoomed in to the pulse unit. You can see probably here, but these are the 3 transitron valves, and here are the neons sitting next to them in the system along the back here. So the sort of size of these, they were about 9 inches by 8 inches by 18 inches deep, with a total weight of about 33.5 kilograms. And you can see a closer look at the construction. This is the receiver. Here is the local oscillator, the mixer valves, and the IF amplifiers, and cathode followers. You can just see down here one of the thermionic detector diodes for the headphone circuit, and for the circuit going out to the pulse unit, which is shown here. This is an underview of the pulse unit, where there was a preset control for the modulation, depth of modulation, and for the length of delay. And here is the transmitter, this is the oscillator, and this is the doubler amplifier. This is in fact an EF50, so a very famous valve, widely used during the war, rescued just in time from the factory in Eindhoven just before the Germans arrived, and they brought back the designs for the EF50, which was very, very widely used just before the war in Pi televisions, but then during the war in the IF strips of nearly all the radar systems. So that's a very simple little transmitter, and this just is the high-pass filter here, from the antenna high-pass filter going through to the transmitter. And then finally, the power supply. Nothing very remarkable to stabilize voltage output. What was important in all these early systems, the early radars and these jammers, was the advent of the engine generators. You'll see later on that a lot of the German radars were still using motor generators driven by 24 volts DC, but these were AC generators which were driven directly off the engine, so often rather a variable frequency of output, but nominally 1500 cycles a second, and then a voltage control panel using a carbon pile regulator to regulate the field windings on the generator to give you a constant voltage out. So, as I mentioned, the spoof signals could be up to 50 microseconds long. It was estimated this was the maximum range extent before adjacent flare signals would cotton on that actually the bearings for these jammer signals were different if they were too range extensive, because they would just be on the same bearing as the aircraft, at two different sites, their bearing measurement wasn't that good, but if it got the range extent was too great, then they would smell a rat. And they fluctuated like real signals. So what we can see here are some 2-mile long signals, actually on a chain home low display, which is about another VHF British radar. And in those days, they plotted range against amplitude, so this is positive amplitude going down the screen like this. And this is a slightly longer simulated jammer response with the different modulation intensities, A and B, depending on the number of targets you were trying to represent. And I just did a little bit of work in Mathematica, and I've generated what I think these sort of responses would have looked like in real time. This is noise, and then you get this range extensive fluctuating signal from the 50 microsecond long jammer response. These reproduce what was seen on British radars. The Germans, they didn't know what kind of displays they had. In fact, they did use A-scopes like this, but they were much more conventional sort of range up the screen and amplitude off to the right or to the left, which I'll show you in a minute. So these early uses of Moonshine were actually very successful. Enemy fighter squadrons, entire squadrons, were scrambled to meet phantom threats, allowing real raids to proceed with a reduced threat. But of course, once the Germans realized what was happening, the inevitable protection measures were put in place. And the first thing they did was increase the range of frequencies that Freya operated on. And so this required then even more of these Moonshine equipments to fly at the same time if you're going to jam a wider range of frequencies. And also they introduced further Würzburg-Riese systems, which could detect targets out to 70 miles. And so this further impaired the ability to jam the Freyas without being detected yourself. They did have a go at refitting the aircraft to bow fighters in 1943, but by quite soon, after the middle of 1943, the requirement to jam Freya like this had actually gone away. The technical situation had changed, and so in fact, Freya, the Moonshine was discontinued as an airborne jammer at that time, 1943. Mandrel, which I mentioned briefly earlier on, which flew quite soon after Moonshine, was this barrage jammer. And these were still very widely used, and lots of different models of Mandrel evolved during the war to protect the bomber raids over Germany. They would go out, carry aircraft with Mandrel to disrupt particularly the Würzburg radars in the German air defences. So Moonshine wasn't used to spoof Freyas after about April 1943. However, the equipment was soon needed again as the Allies planned Operation Overlord, which was D-Day. Now, the intention was to try and use this same equipment, modified, which we'll see, to spoof the airborne, spoof the enemy airborne maritime reconnaissance aircraft, which were used for detecting ships on the sea surface. And the idea was to give an impression of a long line of approaching ships crossing the channel in a different place from where the actual invasion was going to take place. This is going to require equipment operating on a different frequency and also manned by operators. So now the threat would normally just be a single airborne radar, a single airborne maritime reconnaissance radar. rather than multiple flares on different frequencies. So now the Moonshine equipment could be tuned by an operator, tuned across the band, listening for a threat signal, and once he found one, then he tuned the transmitter to the same frequency, all listening on headphones to try and detect the threat signals. For D-Day, as well as these electronic jamming systems for the airborne radars, they jammed the ground-based radars, which were their coastal surveillance radars, by dropping window, what we now call chaff, from Wellingtons. They had Wellington circling around, slowly moving a front of chaff across the channel to make it appear like a slow-moving convoy of ships coming across. And I'll show you what this system turned out to be, but the same idea was going to be used later in 1944 in Operation Dragoon, so a few months after D-Day, when the Allies invaded the south of France. So the naval version of Moonshine was called the Type 660, naval name. Its main threat was the FUG, the Funkgerät radio apparatus, number 200, Hohenwald radar. And it was fitted to German maritime reconnaissance aircraft operating in the band 540 to 590 megahertz. And they believed there were subsidiary threats from something called the Liechtenstein S, which they thought at the time operated about 75 to 85 megahertz. Actually, the books all say it probably operated more like 150 megahertz, but that's probably why they never saw any. But and there was another system called Rostock, about 120 megahertz. And they were also rather worried that they knew that they'd captured British airborne maritime reconnaissance radars, and they might be using these. So they had to be look towards that as well. And in order to show you what these German threat radars look like, I'll first of all show you the British ASV, Air Surface Vessel Mark II design. and basically, this is a Hudson, Lockheed Hudson. They had a transmitter, fixed transmitter antenna pointing forwards, and then two receive antennas squinted left and right. And the idea was that you transmitted a pulse with, through the transmit antenna, and then, or a series of pulses, a stream of pulses, and then the receiver switched between the left and right receiver antennas with a dwell of perhaps about 20 milliseconds to receive a few pulses on each, and then compared the amplitude of the left and right returns to give an indication of bearing. And when the returns in the left and right antennas were the same, the target was dead ahead. So very simple, no steering of antennas or anything. This is what they actually look like. This is on actually a Beaufort, I think. This is the transmit antenna, basically a Yagi array, and here is one of the receive antennas. So this is what the British had, at least at this point in the war, 1942. This is one of the very first German systems, which was called Rostock, and essentially it was the same idea. They almost certainly got the idea from capturing British radars. So this is a slightly lower frequency, but basically a transmit array here. It's about 120 megahertz as opposed to 176 in the British systems. And then two receive antennas left and right, as shown here. And here is their indicator system. And again, they had this tiny little cathode ray tube with a magnifying glass in front of it as their main indicator, 2.5-inch cathode ray tube, using an L-scope display, which I'll show you in a minute. And this was fitted to a Focke-Wulf 200 Condor aircraft, but was replaced in 1943 by the FUG 200 Hohenwald, which was built by Lorentz. This was built by Gemma, this system. And here is the Fug 200 Hohenwald. This is a Junkers 188. These two are the same aircraft. And I don't know whether you can see here, but here is the transmit antenna. This is a higher frequency. This is sort of 550 megahertz, thereabouts. A transmit antenna and then two receive antennas. And here's a broader view of the aircraft. The eagle-eyed amongst you might notice this has an RAF roundel under it. And this was because this particular example was photographed in 1945 at RAF Bryce Norton after it had been captured at the end of the war. And they took a lot of these German aircraft and equipment to evaluate them before scrapping them. And here is a similar installation of the same radar, but on a Heinkel HE-11. I'm not going to dwell on this picture, but this is the block diagram of the Fug 200. But you can see that it had an aerial switching between the left and right receive antennas. It also had side-looking antennas, another idea they got from the British. We can see that on this picture of this Wellington. So here is the forward-looking arrays, but what they also had these side-looking arrays. So this was an array of dipoles along the top of the aircraft, transmitting left and right, a beam left and right as they flew along, and then they would switch between these left and right receiving arrays to sweep an area looking for targets, and then when they found one, they would turn the aircraft and home in using the homing system here. And the Germans developed very similar systems. And again, this is just the parameters. I think the only thing to note perhaps are the peak power, which was very high for this frequency at the time, extremely high. But they only had a 50 hertz, 50 pulses a second repetition frequency. So actually the mean power was extremely low, so it wasn't a particularly high performance radar. But it was a thing of beauty to generate this type of peak power, and I'll show you how they did that in a minute. But very broad antenna beam widths and relatively low gain. Using horizontal polarization. Everyone during the war used horizontal polarization for maritime radars. They found they got too much return from the sea with vertical polarization. Here's just a picture of the indicator unit in the JU-188. This is a patched up bullet hole in the canopy, which they've done some running repairs on. But again, you can see it's very small. Here's the control column and this very small display. And looking in, this is an example, a chap in Germany who has got a collection of these radars, this magnifying glass. And this is what the display would have looked like. This is just a 2.5-inch display. I think yes, the perspective on the screen is squashed. It should be circle, but basically you've got a target day ahead. This is range, and this is left antenna and right antenna, and so targets off to the right would just show on one side, and either side equally like this. And it had an exponential time base. And here is the interior of the Junkers, showing the transmission receiver, and here is the modulator producing these very high power pulses. This is a helium thyrotron, and just get the right numbers. What's my place? it's a helium thyratron. The height of this device is about 7.5 inches, 19 centimeters, and it produces very short pulses with a very high current, about 500 amps, something like that. And again, this comes from the collection of Dieter Weikirch in Germany. So back to Moonshine. They needed to jam this radar, and so the naval version was known as the Type 660, and it operated on a very similar principle to the airborne system, but now with an operator and no AVC memory, because this was very closely, they were going to operate it in a ship on the sea surface. They got a lot of multipath interference and fading, so that you couldn't rely on transmitting back the frequency you received, because you'd go into deep fades every now and then. So they transmitted back a constant amplitude signal. But it basically was the same. It had a local oscillator, a wideband mixer, a slightly different IF frequency, but the same sort of modulation circuits and a similar sort of transmitter. And this was the 55 centimeter version against the Hohenwald, and then lower frequency systems were also produced against the VHF radars. And here's a picture of the equipment. None of these equipments have survived. There's just a few photographs, and this is an extremely rare photograph. This is the naval equipment now in 4 boxes. So they were fitted to harbour defence motor launches, and US Army personnel were specially trained, specially selected and trained by the Telecommunications Research Establishment, TRE, Post-Design Services Team, PDS. And the operator would basically tune across the band until he received a threat signal, and then tune the transmitter to the same frequency. Luckily, the Hohenwald had only had a 50 Hertz PRF, so it was quite distinctive compared with the other UHF radars, the ground-based radars like the Würzburg, which were 500 or kilohertz. They used diversity reception on these at UHF to try and reduce the multipath fading, but at VHF they just used a single tall transmitter mast. So during Operation Overlord in June 1944, it was used in 2 naval diversions, one called Taxable in the Cap d'Antifer region, and Glimmer in the Boulogne region. And 3 harbour defence motor launches were used in Glimmer and 1 in Taxable, and with Moonshine sets covering 540 to 590 and 75 to 85 megahertz. And then in Operation Dragoon in August 1944, the invasion of the south of France, it was used in 2 naval diversions called Lovecast 1 and Lovecast 2 at La Ciotat Bay and another near Nice. They had each of these on different days. They each used 5 harbour defence motor launches with 3 different Moonshine sets covering different frequencies, and as well as these Moonshines, they also had aircraft laying window in the same way. And here's an example, a picture of window, strips of resonant reflective aluminium strip being dropped from the aircraft, and a jammer called Carpet, which was a barrage jammer. And, again, Carpet 2, very rare, sort of drawings of it, no photographs that I could find. But as a result, certainly of the Operation Dragoon, a German radio station reported that during the landings in southern France, a convoy 12 miles long had been repelled in the La Ciotat Bay area. And of course there was nothing there in reality. And so the decoy operations appear to have been very successful. So Moonshine was available in various versions towards the end of 1944. The British ones were built by TRE. They were sort of hand-built, essentially. There are only tens of these ever built. But there was also now an American version, which covered different frequency bands, and this was mainly aimed at being used in the Pacific War against the Japanese radars. Now, work had been started by EMI research labs at Hayes, where I started work, but not at this time. And they'd started work in 1943 on a 55 centimetre version of Moonshine, but that had been discontinued because the operational requirement wasn't there. But some of the advanced ideas from this work were taken forward in this American Moonshine in 1944. And this equipment was called the ANAPQ-15. And I'll just briefly show you what that was. This was perhaps actually the first true repeater jammer. So it had plug-in RF heads covering different frequencies. So the transmitter here, and an antenna, and also acting as a receiver antenna here, mixed down to an IF covering a 5 megahertz bandwidth, and then the pulses were modulated by two quartz crystal delay cells at slightly offset frequencies in the band, and these were quite natty devices. So this is about 2 inches long. This cylinder here. Here's an X-cut quartz crystal where the IF signal is fed in, and this propagates signals through this liquid inside the cell, xylene, or metaxylene, we would call it probably in Britain. But essentially, it propagated through this and then was reflected off these edges on the darker black here. So these edges, and reflected back and then and picked up by the quartz crystal to give you a modulated signal. There were two of them at different center frequencies, but also they had a heater here which heated the xylene, which gave a fluctuating propagation, a variation of velocity of propagation through the liquid to give you the breathing and interference effect of multiple targets. And it was fine, provided they were operated vertically upright. They worked very well. So, to sort of finish off, British Moonshine equipment were first built in small numbers by TRE, first in aircraft to confuse the frayers, and then on naval vessels. They were very effective when first used in all cases, but they then resulted in countermeasures and changes to the enemy equipment. So the frayers expanded the range of frequencies they operated on, and the Hohenwald introduced the ability to rapidly tune in frequency. So he had a reserve frequency he could just switch to immediately. In response to all that, of course, work was underway at the end of the war to introduce panoramic jammer receivers with motorized tuning, and this included methods to rapidly identify new signals and automatically tune to match the frequency of them. And then, even then, more advanced work was just starting on methods to identify radars from their emissions. And so the cycle of countermeasure and countermeasure was well and truly underway, and of course continues to this day. So that's more or less it. If anyone's interested, I've published a number of papers in the IEEE Aerospace and Electronic Systems magazine over the last few years on ASC Mark 1, on the Hohenwald radar, and just very recently on Moonshine. But that's it.
Thank you very much, Simon. Questions?
You mentioned that the Germans had a very small screen and they thought that our equipment was too big.
Yes.
How did the sizes compare?
Sorry, well, we typically used sort of 6-inch diameter cathode ray tubes at that time. And much later on, you know, there were 12-inch systems in some of the American equipment in particular, but mainly 6 inches for us.
Thank you. Simon, could you repeat the question?
Yes.
Sorry, thank you very much for the interesting talk. Are you able to say anything about the work that Alan Blumlein did during the war?
Yes. So the question is about Alan Blumlein, and well, yes, he was an EMI engineer. He filed a patent once every 2 weeks for the whole of his working life. And before the war, he'd filed patents on stereo gramophones, which didn't come out until after the war, and on television. And it was the television work in particular which was taken forward by EMI in designing radars, all pulse-forming networks, oscillators, sawtooth generators, all that sort of stuff, and displays, obviously, was all very important. And Blumlein was involved particularly with the development of the early stages of development of the H2S radar, which is the magnetron radar. In fact, EMI was trying to develop a klystron transmitter, but in parallel with that, the people at TRE were doing a magnetron transmitter, and they had a test flight when they all flew up to look at this new magnetron transmitter, and the aircraft crashed. And then Blumlein and several EMI engineers and TRE engineers were killed.
Okay. You mentioned Dragoon.
Yes.
The jamming was successful, you said, because the Germans thought it was a 10-mile convoy. But this was 2 months after the D-Day jamming ground, not Normandy, but it must have been further up Channel where we were trying to fool.
Yes, it was around Calais. And,
yes, that's right. Well, given that 2 months, didn't the Germans realise that we had this radar, and hence when the Dragoon came along, they thought this could well be a spoof?
Well, but yes, I suppose, you know, it's the usual problem. Is it a spoof or isn't it? Is it real? And they didn't have any way of telling, you know, easily without putting themselves in danger. And so, you know, so clearly, you know, it was only a couple of months later. That's not very long, actually. You know, later on, the Hohenwald were modified so they could change frequency, for example. But they wouldn't have had time to introduce that in that very short time span.
Yeah, on that note, how did they think they had repelled a non-existent attack? If they'd sent up fighters, they would see.
Well, it had gone away, I think.
Repelled by what?
Yes. So the question is, how did they repel? Well, but yes, well, it's one of those things that probably you know, it was a radio report, so propaganda. But they'd obviously detected something, and then later on they realised it wasn't there, so it must have been repulsed.
And then if they didn't do anything,
they didn't do anything. So there's no record of what they actually did. There is record in the first airborne use of Moonshine. They definitely scrambled squadrons of aircraft to intercept these threats. And then, of course, discovered they weren't there.
But if they didn't do anything, then we didn't really have any effect, did we?
Well, it's clearly, well, you know, I don't know exactly, but the idea was to get them to start to worry about whether they got their defences in the right position and move their defences.
Greg, you had a question.
What was the tactical change in 1943 which rendered Moonshine?
Well, I think they were penetrating further into France and Germany with the bomber streams, I think, and so they needed now not they could get over France and going into Germany, but they needed then to suppress the air defence. Then they used window and when it was released and the barrage jammers, simply to put the enemy radars out of use. Spoofing in that way was fine for long range stuff, but this is much shorter range, self-protection.
Okay, you mentioned the helium thyratron
Yes.
as a very powerful transmitter of pulsing. Now, a few years back, we had a wonderful lecture on the magnetron, which we were on Mike here, which we were told was a game changer, very powerful. How does that compare with the helium thyratron?
Well, the thyratron is a pulsing device for modulating. So the magnetrons were also modulated, but I'm not a great expert on thyratrons, but in the early radars they used spark gap. But basically you had a delay line which you pulsed, and then you had a transformer to transform up the volts to fire the magnetron.
It's, if I may...
Yeah, please carry on.
Yes, I took note of the fact it was a helium, because I hadn't realised that the Germans were using helium gas. We weren't using, we were using hydrogen in general in our thyratrons. And I took note of the fact that, I think you said 500 amps?
I think that's what the figure I got, yeah.
Yes, 500 amps, and that was everything. And when I give my talk, I'll probably filter that figure and put that in, because that is quite remarkable. That
Particular thyratron was carried on being manufactured after the war. It was so successful. And,
I bet it did. I have a question, which is a more general question. Simon, how much of this stuff has been released in general, and how much has it been you delving in, as I understand, into the archives? So have we heard some stuff for the first time, so to speak?
Well, I mean,
as a result of that, because the archives were classified.
The archives were classified, but this stuff was probably released in the 1970s, something like that. Okay. But an awful lot of it hasn't really been looked at. So people knew about Moonshine. You can read about the Special Operations Squadron. A lot of work on squadrons and that sort of thing. So they knew that there was Moonshine, but I've never seen before anyone actually writing up how it worked and pictures of the equipment. It's in there, all there in the archives, but nobody had dug it out and shown it to people. So,
well, I think that's terrific. It's well done. Any other questions? Yes, again.
So we had radar, and then the Germans and the Japanese and then the Americans had it. What about, did anyone else, like the Russians, the Italians?
Yeah, I mean, more or less everyone had radar, of different types. The Germans had radar before the war, which we didn't realise. The Japanese certainly did. I'm pretty sure the Italians built radars, how good they were. And of course the Americans built them by the tens of thousands. Stuart,
you can obviously do longitudinal distance spoofing. Can you do lateral spoofing?
Oh well, angle pull-off is tricky, and so what you would if you knew they were doing sequential lobing to get bearing, then you could alternate higher and lower amplitudes signals, but it's not straightforward.
Right. One more. Were jammers used for self-defence of the individual aircraft, or were they always used for deception purposes?
Well, yes, in the examples here, they were certainly the spoofing like that is much more about protecting a fleet of ships or whatever. They they were essentially used in self-defense when the bomber streams went over Germany, because they had jammers which were basically trying to put so it wasn't an individual aircraft but a whole stream of bombers trying to put the enemy air defences out of action by putting up lots of window and blinding them and noise jammers.
Right, I'll ask another question. So you're doing distance spoofing. So why wasn't the tactic to just fly to the closest end, or could you sort of make the aircraft look as if it was further forward than it really was? Because otherwise, presumably, you just fly to the beginning of the jammer signal.
Well, if you've just got an aircraft, then the radar will see one aircraft. But what he's got then, what he actually sees then is an aircraft with a whole series of aircraft behind him, which are the spoof signals. And so they're always downrange. If you do uprange jamming, you need to be a lot more sophisticated and predict when the enemy is going to produce his next pulse. And in those days, radars weren't clockwork by any means. You know, the pulses came out at approximately the same frequency, but they were pretty random. And
I didn't realise that these great long pulses were used in those days, which of course you could use it, and that presumably accounted for your 12-mile long convoy.
yes, exactly. I mean, a modern jammer, if you had a very high resolution radar, you would have to introduce individual realistic targets spaced out, you know, in range. But the resolution in range was so low in those days, less, you know, a couple of hundred meters or something, then we wouldn't necessarily expect to see individual aircraft. You would just see a long range extensive returns.
Right, if there's no more questions, it's just for me to ask you to thank Simon for a really very interesting talk, and as said earlier, releasing material which has never seen the proper light of day before. So thank you indeed on that. And two things before you show the appreciation. I want to show the appreciation. You've got a little certificate here, and a little gift which you can have. And the other thing to say before we show our appreciation is, if anybody hasn't signed the book, the piece of paper, have you got it, Norman? It's there. Please make sure you sign it. And thank you all very much, and let's show our appreciation to Simon.